Hello, this is Jack Jackson. Today we're going to be talking about geometric series. First I want to review a little bit about geometric sequences. Remember that a geometric sequence is an exponential function with a domain restricted to the natural numbers or the whole numbers. Remember, if we let b be a sub k divided by a sub k minus 1, or in other words y2 divided by y1, this is the base of the exponential function. It's also, as you see, the common ratio between successive terms. Often texts use the letter R for common ratio here instead of B, but we're going to reserve the letter for the rate of growth, the relative rate of growth, which is R, which is B minus 1. So unlike general exponential functions, we don't have any problem with a negative base for geometric sequences, because if you remember, our problem with a negative base on the exponential functions is that we had to be able to allow any power, including like a half power or 0 power, some things where the base, where it would be undefined. So we want to be able to do this for all the possible inputs we want to be defined. Well, our possible inputs here are only whole numbers, or maybe even just natural numbers, so those are defined when we have negative bases, and so negative base will be allowed here. A base of 0 would be kind of boring. All the terms after the first one would be 0, and a base of 1 would be kind of boring because all the terms would be the same as the first one. So recursively, we have a sub k is b times a sub k minus 1, and of course, a recursive definition, you'd also have to identify some initial term. Non-recursively, we have a sub k equals a1 times b to the k minus 1, or if you figure out a 0th term, it would be a sub 0 times b to the k. And of course, a sub 0 is just a1 divided by b. So for example, if a1 is 3 and b is 2, then the domain, the x's or k's are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. And they go on forever. A sub k would then be 3, and then 3 times 2 would be 6, times 2 is 12, times 2 is 24, and so forth. Oftentimes, this, remember, for sequences, we just write the outputs, so this might just be written as 3, 6, 12, 24, and so forth, written like this, which are, of course, just the outputs of this. The inputs up here are automatic, 1, 2, 3, 4, 5, etc. So, let's just practice this a little bit. Here's an exercise. So given the sequence 5, 10, 20, 40, 80, 160, write out the next 6 terms of this sequence. Okay? What type of sequence is it? Write a recursive formula for the kth term and a non-recursive formula for the kth term. And then what is the 31st term? So this is review material. You should be able to do this now. Do this and then come back and we'll check your answer in just a minute. Press pause now. So here are the solutions. Notice that each time we're multiplying by 2 to get the next term. So this is a geometric sequence. The common ratio is 2. And so the next 6 terms are, we just multiply by 2. 160 times 2 is 320, times 2 is 640, and so forth. By the way, here's a nice easy way to do this on a calculator. You can start with 5, hit enter, and then say times 2, which will take the previous answer times 2, and then just hit enter again, it'll take the answer times 2, and so forth, and we can work it out like this, and then just hit times 2, times 2, times 2, times 2, and so forth, and we can work our way up to eventually to the ones that we need here, like this, and then go on down to the ones we need here. And so that's an easy way to get this out of the sort of a recursive pattern like that. We can work that out very nicely, at least if it's one basic operation over and over again. If we're going to repeatedly add the same number each time or multiply by the same number each time, you can do it pretty easily in the calculator like that. So this is a geometric sequence. Recursively, a formula has 2 parts. The first term is a1, which is 5, and then a sub k is 2 times a sub k minus 1 for all the k's bigger than 1. Natural numbers, of course. and write a non-recursive formula for the kth term. That's an exponential function formula, so it's initial term 5, 2 to the power k minus 1. So this is centered at the point 1, 5. So there's sort of our point base formula. Okay, the base is the common ratio. What's the 31st term? Just plug in 31 in that version. So we've got 5 times, well, 31 minus 1 I can do in my head, that's 30. So 5 times 2 to the 30th, you can see on the calculator there, gives you this 5,368,709,120. So next, let's do the next problem here. And let me get this down to one page here. So find the, we were given a geometric sequence with initial term 2 and common ratio 3. Write out the first 6 terms of the sequence, then find recursive and non-recursive formulas in the 20th term for this sequence here. Press pause now. Okay, hopefully you're back. And here I use the little shortcut thing to work this out very easily. Of course, it's not too hard to do by hand. 2, first term, times 3 is 6, times 3 is 18, times 3 is 54, and so forth. So recursive formula is a1 is 2, a sub k is 3 times a sub k minus 1 for k is bigger than 1. Non-recursively, that's a sub k, or y, is 2 times 3 to the power k minus 1. So the 20th term, plug in 20 for k, that's going to be 2 times 3 to the 19th power, which I did on a calculator here, and got this. I could have done that by hand, but it would take me quite a while to keep multiplying by 3 19 times. So the calculator was a pretty nice welcome shortcut there. Alright, so all that's review. Now let's talk about a finite geometric series. So in general, remember that a series is the sum of the terms from a sequence. So a geometric series is the sum of a geometric sequence. So we'll let S sub n stand for the sum of the first n terms. Now recall that when we study linear functions, we were able to derive a little shortcut formula for finding the sum of a finite arithmetic series. And so we similarly want to do something like that to find the sum for a geometric series. Now, of course, this is not arithmetic, this is geometric, so the same little technique that we use there for finding the formula for arithmetic is not going to work, but it turns out there is a nice way we can find a formula for a finite geometric series, and we're going to work that out here in just a minute. Okay, and in this case, the first term is going to be a1, and the 0th term, a sub 0, is not really part of the sum. It's not really part of the sequence, part of the series, but we might refer to it if we wanted to, which is the first term divided by the common ratio, or the base b. And in the notation below, you're going to see this first line right here. This line here gives you several different ways you might write the sum out. Remember, we use this capital sigma for meaning add them up for the sum of some kind of series. So we're adding the term a sub k, the first n terms from 1 to n. So that's going to be called S sub n. Another way to write a sub k is a sub 0 times b to the k, if you figured out this non-existent 0th term. Or it's a1 times b to the k minus 1, which is a formula we just used above. And here you can change the sum. If you go from 1 to n, you can also go from, say, 0 to n minus 1, and now the power j is k minus 1, so the power is just j here. So those are different ways that we can do it. And it turns out that the answer is going to be, we're going to prove this in just a second, but the answer is a1 times 1 minus b to the n over 1 minus b. So b, again, is your common ratio, dividing one term to the next, or what you multiply by to get one from one term to the next. N is the number of terms that you have, and a sub 1 is the initial term. Now, you can also multiply top and bottom by negative 1 to get it in the second form here. Usually you'll see this written in the first form, and the first form is probably better if you've got a base that's between negative 1 and 1, so that both of these numerator and denominator are positive. If your base is bigger than 1, you might choose to write the second version, which gives you a positive in the numerator and denominator. Doesn't really matter. Don't need to memorize both versions, just one or the other. So here's the proof. We're going to assume the base is not 1. And if you think about it, this formula that's up here will not work if the base is 1, because then you get 0 over 0. So this is undefined. But of course, if the base is 1, then all the terms are the same. And actually, if you're adding them up, you just get n times whatever that first term is. And that's not really a geometric series. It's like a constant series that you're adding up. So we're not going to worry about b is equal to 1. So if b is not 1, then we're going to take 1 plus b squared plus, so forth, up to b to the n minus 1, and we're going to multiply by 1 minus b. Well, if you multiply everything by b, all the powers go up 1, but it's minus b, so they're all negative now. So negative b times 1 is negative b times b is negative b squared, then you got negative b cubed, negative b to the fourth, and so forth. And the last one is going to be negative b to the n. The one before that is negative b to the n minus 1. When you multiply everything by 1, they stay the same, but if I line up like terms, they line up like this. And if you notice, all of these middle terms, you're going to have one positive and one negative, so they cancel out. And the only thing left standing is this 1 at the beginning, and then the minus b to the n at the end. So if you write that out this way, you see that basically all we used there was just the distributive property, the same way we use just to do multiplication of multi-digit numbers. We're using exactly the same algorithm there. So down here we have 1 plus b squared and so forth up to b to the n minus 1 times 1 minus b turns out to be 1 minus b to the n. Now we're going to divide both sides by 1 minus b to get this version here. And now we're just going to multiply by the first term, a1, to get this. And when we distribute on the left, we get a1 plus a1 times b plus a1 times b squared plus and so forth. And in fact, that is exactly the sum of a1 times b to the k minus 1 from k equals 1 to n. Okay? And that's exactly the sum of the first n terms of a geometric series, with a1 being the first term and b being the base or the common ratio. And so there's our formula, and we have derived that. So here's our formula. The sum of the first n terms of a geometric series is the first term, a1, times the fraction 1 minus b to the n over 1 minus b. N is the number of terms that we're adding up. B is the common ratio, or what we're multiplying by each time. It's our base. Okay? So take that formula and let's apply that. You might want to jot that down. Okay, and let's apply that in this next exercise. We want to, actually it's a series of exercises. We want to find the sum of the first 15 terms of a geometric series with initial term 3 and common ratio 2. And we're going to find the sum from 1 to 25 of 1 over 1,000 times 2 to the k. And the next one we're going to find the sum from from k equals 1 to 42 of 1/100th 1/2 to the k. And I think we're going to stop there. So go ahead and work this out. Come back when you've finished. Press pause now. Well, when we look at the solution here, we're just using this formula. S sub n equals a1 times 1 minus b to the n over 1 minus b. If its first 15 terms of a geometric series has initial term 3, so that's a1 is 3. Common ratio is 2, that's our b. So just plug that in. 1 minus 2 in the denominator is negative 1, so distribute that in the top. You get 2 to the 15th minus 1. So it's 3 times 2 to the 15th minus 1. Here I use a calculator to help me out, and that's 98,301. In the next example here, I have the sum from k equals, let's see, that's A. Where's B? Here's B. Okay. I want to take this one, and I've got the sum from k equals 1 to 25 of 1,000th k 2 to the k. So we're going to use the same formula, but this time we need to figure out what the first term is. So I need to plug in k as 1. K is 1 gives me a 2 here, so I get 2 over 1,000 for the first term. Then my base is 2. So this is the kind of thing that you're multiplying by 2 each time. So this is exactly what makes you see this exponential formula here. So that's an exponential sequence, or we call them geometric sequences. So in the denominator we get 1 minus the base of 2. The top we get 1 minus the base to the power is how many terms we have. Well, 1 to 25, that's 25 terms. Okay, again, 1 minus 2 is negative 1. Distributing the top, we get 2 to the 25th minus 1. 2 over 1,000 is 1 over 500. So I just did that in my calculator, and that's an exact value there. 67,108.862. And the next one here, we have the sum, again, very similar kind of setup. This one, when k is 1, you get a half here times 100 is 1 over 200, so that's your first term. We have 42 total terms here with the base of 1 half, so it's 1 minus 1 half to the 42 over 1 minus a half. 1 minus a half is 2. Multiply top and bottom by 2 here to get that down to 1, which I'm going to bring that 2 out here actually. Cancel the 2 on the 200 down to 100, or half of 200 is 100. And then we got 1 minus a half to the 42 power. Well, if you did this on your calculator, 1 over 100 times 1 minus 0.5 to the 42, it just comes out to be 0.01, and so it's approximately 0.01. So basically it's saying that this thing here is approximately 1, so this 1 half to the 42 is approximately 0, and it is approximately 0. Notice I did it here, 0.5 to the 42 power, and I got 2.27, etc. That e negative 13, remember, is scientific notation for times 10 to the negative 13. So that's a point, 12 zeros, and a 2. Subtract that from a 1, it looks like a 1 here, but it's really point 12 nines, and then 772626326325, and then divide by 100, moves it over 2 more places. So here's what it is out that many decimal places. But of course that rounds off to 0.01, at least up to many, many places there. So it's approximately 100th. It's actually just slightly under 100th, but it's very close to that. So we're going to apply this. You may see some homework problems where this is applied in real-world problems. And later on, we're going to be using this. In fact, one of the main reasons I wanted to cover this is we're going to use the sum of a geometric series to derive formulas for mortgages and annuities. So we're going to, so things like figuring out car payments are going to need this sum as a key step in deriving the formulas for that. So we'll see that in our last section of this unit, and it actually is going to kind of combine the idea of geometric series along with this idea of compound interest. So we'll come back to that a little bit later. Now there is something really kind of interesting here that's kind of a neat idea that we didn't get in the case of an arithmetic series. In the case of a geometric series, it actually sometimes makes sense to talk about adding together all of infinitely many terms. This works if the absolute value of b is less than 0. So when this happens, the b to the n in this formula up here, let's look at our formula. There's our formula. Well, if you take just the b to the n part, if the base is between negative 1 and 1, exclusive, then when you raise it to higher power and higher power and higher power, we know that that approaches 0. We've seen this in our study of power functions, okay, and exponential functions, okay, and properties of exponents. So that's going to go towards 0. So what's going to happen is if we can say that the limit of this sequence as n goes to infinity is the b to the n goes to 0, and so that term basically just disappears, and then the formula reduces to this. A sub 1 times 1 over 1 minus b. It's actually a simpler formula to add up infinitely many of these things than it is to just add a finite number. But this only works if the absolute value of the base is less than 1. So if the base is bigger than, say if you got a positive a1 and the base is bigger than 1, then this actually is going to add up, then the sum is going to actually approach infinity, like it would normally do when you add up infinitely many things. But since the things that we're adding each time are smaller and smaller, getting closer and closer to 0, it actually turns out that we can add up an infinite number of things and actually get a finite answer. That's pretty bizarre. And this is a solution to an ancient paradox. There's an ancient philosopher called Zeno, and he was an old Greek guy, and he recognized there was an idea that he that's been known as Zeno's paradox. And it basically goes like this. He proposes that you have a race between the famous hero from Greek mythology, Achilles, and a tortoise. Okay? So clearly Achilles is much faster than the tortoise. So Achilles is going to give him a head start. And let's say he goes halfway to the finish line. Now consider the race in stages. At the end of the first stage, Achilles makes it to the position where the tortoise was. Okay? Actually, let's say he makes it to the position of the tortoise, halfway to the finish line. However, in the time it takes him to go there, the tortoise is going to be moving some slower speed, of course, but it's going to still move some. So the tortoise is moved forward. So Achilles is behind still. Well, at the next stage, Achilles makes it to this new position of the tortoise. But again, the tortoise is moved forward. And each stage of the thing, Achilles makes it to the position of the tortoise, to the previous position of the tortoise, only to find that the tortoise has moved forward even more. So it looks like it's impossible for Achilles to ever catch up with the tortoise. But we know in reality Achilles could catch up with the tortoise, so this creates a paradox. Well, the solution to the paradox is to notice that it will take an infinitely many stages for Achilles to catch up with the tortoise, but the sum of the distances traveled in these infinitely many stages is actually a finite distance, and the sum of the infinitely many times that it takes to do these stages actually sums up to a finite time. So even though we've divided the race up into infinitely many parts, these parts add up to a finite distance traveled in a finite time. Therefore, Achilles can catch up with the tortoise. Of course, we knew he could. So this is basically the idea of what's happening when we're summing an infinite geometric series where the base is close to 0. So, let's see if we can apply that formula. Let's review the formula real fast. You might want to jot it down. It's the sum of infinitely many terms is a1, the first term, times 1 over 1 minus b, where b is the base or common ratio. And that's this only works. It works if and only if. That's what IFF stands for. If and only if the absolute value b is strictly less than 1. Okay? Essentially like a proper fraction or a decimal number close to 0 there. Okay? So use that formula and figure out the solution to these exercises. Compute the sum of an infinite geometric series with initial term 4 and common ratio a third. Compute 1 plus a half plus a fourth plus an eighth and so forth. And then compute 5 times 0.02 to the k from k equals 1 to infinity. When you finish this, come back and we'll check your answers. Press pause now. So here's the first one. An infinite sum of an infinite geometric series. So we're adding together infinitely many things, but notice we'll come up with a nice finite number, actually 6. So initial term 4 and common ratio is 1/3. So we're adding 4 plus 4/3 plus 4/9 plus 4/27 plus 4/81, etc. And we're adding up all infinitely many of these things. So the first term is 4, and the base is 1/3. So 1 minus 1/3 is 2/3. 1 over 2/3 is 3/2. 3/2 times 4 is 6. So that sums up to 6. Okay. The part B, we're adding together 1 plus a half plus a fourth plus an eighth. You notice the first term is 1 and the common ratio is 1/2. So this can be written as k equals 0 to infinity 1/2 to the k. And so this is 1 times 1 over 1 minus a half. 1 minus a half is a half. 1 over a half is 2. So this reminds me of a joke I heard. There was a mathematician's convention, and so a bunch of these mathematicians went down to the bar. The first guy orders a pint of beer. The second guy walks in and orders a half a pint of beer. The next guy orders a fourth of a pint of beer. The next one orders an eighth of a pint of beer. And the bartender says, wait a minute, I see where this is going. So he pours 2 pints of beer and serves them. So, in this next example, we've got the sum from k equals 1 to infinity of 5 times 0.2 to the k. So notice when k is 1, 0.2 times 5 is 0.1, then we're multiplying by 0.2 each time. So then it's 0.02 for the next one, 0.004 for the next, 0.0008, and so forth. But we're adding up all infinitely many of these. Notice the first term is 0.1, and the common ratio, or the base, is 0.2, and this is a geometric series. So it's 1 over 1 minus b times the first term. So it's 0.1 times 1 over 1 minus 0.2. 1 minus 0.2 is 0.8, and then see that, so it gives you 0.1 over 0.8, which is 1/8, or 0.125. Alright, so that should give you enough that you can be able to apply these to some of the problems. Some of them may be real-world examples, and some may be just computational examples in the homework. And like I said, the main thing I want is from this is we're going to apply this to some real-world things a little bit later on.